a photo. Okay, 1, 2, 3. Okay. Okay, so allow me to share my. Okay. Just a recap of what transpired earlier this afternoon, as mentioned by Director Hidor. We had just completed the poster session of the Graduate Research Colloquium, and three students, one master student from transportation engineering, one from structural engineering, and one PhD student specializing in geotechnical engineering delivered a poster presentation. So you can see here the topics that were presented earlier in the poster session. So now we are on the online session, and we have three presentations, all from graduate students who have recently completed their studies. Okay, so just a couple of reminders to the participants. So all the three presentations will run continuously and to be followed by a question and answer session after all the presentations have been delivered. Okay, so please use the Q&A feature of Zoom for your questions. Because of the limited time in the Q&A, we may not be able to cover all the questions live. And in that case, we will ask you to input your questions to the feedback form that we will also give a copy to the presenters. Okay, and yeah, with the feedback form, that will be flashed at the end of the colloquium. So we would like to ask you to accomplish that so that we know your thoughts, and we always strive better in delivering interesting talks in the Graduate Research Colloquiums. Okay, so I think you can already start with the presentations. About our first presenter, Engineer James Godfrey L. Sagid has completed the requirements for his Master of Science in Civil Engineering at the University of the Philippines, Diliman, specializing in structural engineering. His thesis aims to address the challenge of fluid structure interactions, an area critical to infrastructure vulnerabilities. Despite its importance, the field has room for improvement, as existing modeling techniques may not fully capture the complexities of these interactions. Driven by a strong inclination toward research and innovation, James is dedicated to developing alternative solutions to these complex engineering problems. While completing his graduate studies, he worked as a civil engineer for the city government of Antipolo, contributing to the assessment and planning of public infrastructure projects. Okay, so let's listen to James Sagid's presentation. James, let me start your presentation when ready.
Good afternoon. I am James Sagid, MSCE Engineering. Here is my presentation on developing a discrete modeling scheme for fluid structure interactions. Here are real examples of structural failure, sloshing fluid inside a tank, a dam collapse, and damage from typhoons. This reminds us that our model must capture fluid structure interactions. Continuum-based methods are widely used for fluids. They conserve mass and momentum and are the basis of many CFD tools like OpenFOAM and SU2. But with moving boundaries or free surfaces, they need mesh adaptation or interface tracking, increasing complexity. On the other hand, for solid mechanics, FEM is the go-to method for analyzing stresses, deformations, and material responses. But when structures experience significant deformations, or when the load itself changes with the orientation of the structure, formulation becomes nonlinear. and handling the contact adds a lot of complexity to the simulation setup. So why do we have to rethink FSI simulations? Traditionally, FVM or finite element methods and finite volume methods work well individually, but when combined for large deformation problems, the setup can become complex and sensitive to geometry changes. So I explored an alternative, the use of rigid blocks for solids and particles for fluids. So it reduces the setup effort while staying adaptable. So for the combining of the models, one way to combine the analysis methods for fluid structure interactions is the monolithic approach where the fluid and the solid domains are solved as a single system of equations. These tend to be stable and accurate, but it's hard to modify if the need to modify arises. In contrast, the staggered approach solves each domain separately and exchanges data between them. This makes the method easier to adapt and modular enough that we can mix and match different solvers. So why am I interested in the staggered approach, one might ask? The staggered approach handles fluid and the solid separately and links them together. So this makes it easier to set up and adapt compared to monolithic methods. Now delving into the specifics of the methods themselves, the structure uses MRBSM, replacing thousands of finite elements with a few rigid blocks connected by springs. For the fluid, SPH is used for the fluid. So the fluids are converted into particles that carry mass, density, and other parameters, and the symmetry of the system help conserve momentum. So for the coupling of the models, this shows the simulation setup. The solid is modeled as a spring mass system, and the fluid as a collection of particles. These two are combined using a staggered coupling approach, allowing us to reuse already existing methods and instead focus on how we define the interaction. So my main goal for the study was to combine these two methods, the modified rigid body spring method for solid and smoothed particle hydrodynamics for fluid. Since both involve motion, their effects can be translated as forces defining the interface. I then tested how the parameters affected the results. So why it might work? What is significant about this? So I found that it is significant to turn my attention to this as this simplifies the solid and the fluid mechanics problem into a particle and rigid body kinetics. It's not trying to compete with FEM, but rather it's an alternative that is much simpler to set up, making it more suitable for certain types of problem where speed and flexibility matter more than detailed resolution. So here are the scope and assumptions I used in the study. To simplify, the fluid is treated as homogeneous, incompressible, and Newtonian, with the particles being uniform. The solid is also treated as homogeneous and isotropic, and with the rigid bodies being uniform in properties as well. Finally, the simulation or the system as a whole is limited to fluid within the computational domain, in that anything that exits the computational domain is no longer tracked. So here is a quick glance at the conceptual framework. While here are the ideas behind the study. In 2015, Guan developed a single body column model using RBSDM. In 2016, in my undergraduate, I extended it to multiple rigid bodies. I applied axial deformations and material deterioration. Elastic materials are converted into rigid blocks with this concept, and the properties or their elastic properties are lumped into the springs that connect them. On the other hand, for the fluid, smoothed particle hydrodynamics or SPH was introduced in 1977 for astrophysics and adopted in 2003 by Mueller and Associates for free surface flows. The core SPH function estimates values like mass, density, or pressure from nearby particles, while the forces themselves are defined from pressure and viscosity equations. For the coupling of the system, or the combined phase as a whole, a previous work done by Antochi and colleagues in 2007 focused on using SPH for both the solid and the fluid phases. Using SPH for both allowed them to go for a monolithic approach in their coupling. So here, they also performed a water column collapse experiment. This is their experimental setup. a glass box with one of the faces replaced with rubber to act as the flexible element to be analyzed. Here is the result of their simulation side by side with the experiment setup they used. And here they track the free end of the rubber as well as the water level height. Now here is the methodological framework. I'll quickly show how each method was verified and validated before combining them. For the MRBSM, this is the present formulation which I used, which is an expanded version from my undergraduate from the previous study. I won't go into details here, but this equation here governs how the assembly responds. It uses the harmonic equation as shown. On the other hand, this is what I use in verifying and validating the MRBSM. I use the ASTM D412 or tensile test for rubbers and elastomers. I recorded the stress strain curves, and then I applied regression to come up with the modulus of elasticity function that estimates the material properties set. So here is the test configuration. Here is a sample result stress strain curve. Here are the data gathered along with the regression equations defining them. And then here, I took one of the specimens, compared with my simulation, and got this resulting graph. So we see here, the number of components is also designated. And then repeating for the other two samples, we see here that indeed the simulation output lies between the three sample data. For the fluid validation and verification, these are the equations that describe the SPH model I used. And again, I won't go into detail. These equations calculate the forces between the particles and are derived from pressure equation of state and viscosity using relative velocities. For verifying and validating the SPH, I referred to a 2012 study by Violu where they performed the water column collapse experiment. They record the displacements and converted the parameters to be dimensionless to normalize their results. So I validated the behavior using published data as benchmark. Here is the configuration on the left side, while here are the results of running the SPH algorithm at varying pressure proportionality K. So I've chosen to track the top right corner so as to better visualize the effects of changing the pressure proportionality. And here we have the position of the said particle in the graphs shown there. So finally, after establishing that the individual methods work on their own, I then started coupling them. Here we see my CPU and GPU specs. I've used the C language leapfrog integration for stability. I used uniform time intervals for simplification, and the staggered coupling approach, or alternating between the methods throughout the solving process. So here is the schematic diagram showing the simulation sequence. Both models start from initial conditions, as we can see from the boxes marked 0. But only the fluid simulation runs first. SPH computes position, velocity, and acceleration of each particle. These outputs can then become external loads through calculation, as to be shown later. And then with the introduction of the loads for the solid model, we can then calculate using MRBSM to calculate for deformations and reactions. These deformations and reactions will then dictate the new boundary conditions to be used by our fluid model, completing the cycle. So here's a quick recap of the process I discussed earlier. And now here is the corresponding experimental setup I used in the study. I used a base-supported rubber wall instead of a top-supported system, as in Antochi and colleagues' work, so as to produce my own experimental data, as well as to take a step closer to simulating flooding events. So for the coupling itself, I tested several force calculation methods. Inertial forces, or the use of particle accelerations, impulsive forces, or the use of velocities and contact time with the wall instead, quasi-static approach, or snapshotting the system at very small time intervals, and then performing hydrostatic analysis at each interval, And then a method suggested by Lobovsky and Groenenboom in 2009, which was used for an SPH-SPH system. Now, here is the plot showing the result of the simulations using the force calculation methods I've tried, the 4 calculation ones. We see here that the quasi-static approach was the only one that managed to fully simulate the experiment. Now, after checking to see which of the methods I can use for the study, I then tried running the simulations at varying number of components first. With this, I was able to observe that from a one-component model of the MRBSM, the accuracy of the simulation improves up to a certain level, at which it rapidly falls off. Here is the same graph, this time showing only displacement values matching the available experimental data. This more clearly shows that the 3-component model has apparently the best simulation of the component counts used, but it's just apparent for now. Now here, checking the error values, it can be seen that indeed the 3-component model has the lowest peak deviation, while the 5-component model has the lowest average deviation, all while staying within the 5% acceptable root mean square error. Now, after checking the horizontal displacement of the wall, I also checked the remaining water level in the container. There were no significant variations in the simulated water level across the number of solid components. Finally, I also checked the analysis duration while holding the particle size constant, which consistently ran for about 11 minutes. Now, after confirming that the 3-component model performs acceptably, I tested different fluid particle sizes. Doubling the 5 mm diameter to 1 centimeter caused an overestimation of the displacements and missing the peak occurrence as well. On the other hand, having it to 2.5 mm significantly underestimated the displacement, but it does capture the time occurrence at which the peak displacement happens. So I also checked the water level over time. I found out that the fewer number of particles cause early inaccuracies, but later match the correct level. Well, all in all, the particle sizes eventually approximated the same value. Now, I also checked the runtime since particle count strongly affected calculation time as with other discretization techniques. The semi-logarithmic graph shows a duration increase. The duration increases rapidly as particle size decreases from about a minute with the large particles up to nearly 3 hours with the smallest particles. Here is the experiment snapshot compared with their simulation counterparts using 3 components. So I've tested and I ran for about some 2 seconds. It's quite quick. And finally, here are the conclusions I've drawn. The MRBS-MSPH model sufficiently simulates a hydrostatic SSI case. Particle size strongly affects the duration. We have also seen that the effects of the increase of rigid body components in that increasing the number of components improve the accuracy up to a certain extent, from 1 to 5 blocks. We saw that the accuracy dropped by 6 elements, and then the calculation became unstable at 7. But the runtime was mostly unaffected. For the calculation of forces, the quasi-static force calculation worked best. So applying hydrostatic at small time steps. Other methods didn't perform well, though the inertial and the impulsive methods may warrant further study. I will discuss that later. So to summarize the advantages, this method is modular. I didn't need to derive SPH nor MRBSM equations from scratch. I only had to derive the interface equation to be used, as in the quasi-static approach. Each method can be swapped independently, which is a major benefit of the staggered setup. This also ties into the second point, that the separate methods are self-contained in that the SPH results, so just needed the results, the SPH results fed into the MRBSM and vice versa, without them having to access one another's intermediate steps. Finally, this is a new and alternative approach to what we are used to, so we can counter-check against other methods. To close, I'd like to share some areas for improvement. First, MRBSM is a multi-degree of freedom system. More blocks create more vibration modes, which may affect accuracy. Better dynamic analysis could address this. The second one is that the current model only considers fluid particles in direct contact with the wall. This narrow detection radius simplified things but led to an underestimated displacement. Increasing the detection radius may improve the results but would require kernel recalibration throughout the system. Lastly, this study focused on a hydrostatic case. So the framework could be extended by combining quasi-static and dynamic methods to possibly model fluids in motion as well. Thank you and good day. Yun lang. Stop.
Okay. Thank you, Engineer Sagit. Yes, to the attendees, if you have questions, please use the Q&A feature of Zoom, and we'll check that later. So, okay, 1, 2, 3. Okay, I would like to present the certificate of appreciation to Engineer James Godfrey Sagid for sharing his research expertise in the 2025 Graduate Research Colloquium given this 25th April 2025 at the Institute of Civil Engineering, University of the Philippines, Diliman. Signed by Dr. Jose Regin
of what
F. Regidor.
transpired earlier this afternoon, as mentioned by Director Hidor. We had just completed the poster session of the Graduate Research Colloquium, and
Okay, moving on to the next presentation. So about our second presenter, Roydon Jude S. Samudio earned his Master of Science in Civil Engineering, specializing in structural engineering from the University of the Philippines, Diliman in 2024. As a licensed civil engineer, he previously worked as a junior structural design engineer at RB Sanchez Consulting Engineers in Ortigas. In 2021, he served as a faculty instructor at the Technological Institute of the Philippines, Manila. His master's thesis focused on structural health monitoring and the dynamic characterization of transmission towers, advocating for the development of a Philippine-specific design guide for transmission tower structures. His research interests include damage detection using sensor technologies and the promotion of disaster-resilient infrastructure in the country. At present, he serves as Instructor 3 at the Faculty of Engineering, University of Santo Tomas. Okay, so let's hear the presentation of Jude. Hey, Jude, you may start your presentation when ready.
So thank you, Doc. Wait, I'm going to share my screen. Okay, so can you see my screen now?
Yes, you may start.
Okay, so good afternoon, everyone. So I am Jude, and last year I had the opportunity to share the progress of my research, and now I am going to present my completed work again to you all here in this online session. So the title of my research is the application of machine learning-based stochastic subspace identification for automated model analysis of transmission towers. So this work was completed under the mentorship of Dr. Jaime Hernandez Jr. Okay, so let's start with the bigger picture. Why was transmission tower is chosen for this study? So despite being critical lifelines in our power infrastructure, transmission towers remain one of the most underexplored structural systems in the Philippine engineering research. These structures are classified as essential facilities where they face constant exposure to extreme winds because of their remote location, and also they are also exposed to human-induced threats like component theft or explosive. So looking at these numbers, it is evident how vulnerable these structures are. Okay, so from the structural engineering point of view, these towers are classified as flexible structures, making them sensitive to wind-induced dynamics. Numerous efforts were conducted to study its structural behavior, especially under the effects of severe wind conditions. However, with the advancement of sensor technology, the structural health monitoring of this structure has gained traction over the past years, which improves visual and risky inspection. Now, discussing the structural health monitoring process, according to Ritter, we have 4 levels of damage detection, with the first level as detection. To perform this first level damage detection, or what we call anomaly detection, vibration-based structural health monitoring is usually employed. And under vibration-based structural health monitoring, we have the OMA, or operational model analysis, where we can be able to extract the model parameters of the structure, including the frequency, damping ratio, and mode shapes, even without excitation input. Now, under the OMA, one specific technique is what we call the stochastic subspace identification. So it is widely used for its accuracy and automation potential, but the traditional method of SSI faced challenges, including the presence of spurious mode, even the use of stabilization diagram. The second, the need for manual stabilization diagram comparison. And the third, the subjective selection of critical control parameters like the system order N and the black rose I. And these SSI challenges have been demonstrated by recent and very limited OMA studies of transmission tower using SSI, including the study of Lee et al. In 2020 and also the study of Su et al. Also included the study of Xingji et al. In 2021 and the study of Feng et al. In 2024. Also included is the study of Zhu et al. In 2020 for a 28-meter high tower in China, which was monitored during Typhoon Haima or Typhoon Lawin in the Philippines in 2016, where a system order of n is equal to 60 was selected after testing various values and observing the stabilization diagram and selected a block size of 4,096 points for a 10-minute segments. That's why it is important to recognize the need to examine more advanced and scalable techniques. Okay. So recent studies have made significant strides in addressing false modes identification by employing advanced clustering techniques on stabilization diagrams, including the studies shown in this slide. However, several authors highlighted that these studies mentioned from the previous slide still did not fully address the automated selection of the control parameters. So to address this gap, the solution is to simulate different in as many number of sets of this parameter, which is a tedious task that often leads to the use of more advanced techniques. So in 2022, Zhu et al. Introduced a more extensive method by employing a Monte Carlo-based technique to sample different set of control parameters such as I and N, and in 2023, Zhu et al. Improved their existing method to automatically identify closely spaced modes and combination of these two parameters by using XGBoost alongside dbScan, which are all type of machine learning methods. And in 2023, Rose et al. Expanded the work of Zhu et al., still using a Monte Carlo approach but incorporating 4 control parameters now. Given the large number of simulation, they used the random forest, a type of machine learning, to classify and predict feasible sets. So this method was first applied to a high-rise tower in 2023 and later extended to a suspension bridge and masonry building in 2024, demonstrating its versatility across different structural typologies. While RF method produced robust results, the literature did not explore the computational advantages of using this model compared to other machine learning methods. Hence, this study explores the need for a clear result comparison to establish random forest superiority over other models, building on the claims made by various authors in using different machine learning techniques for validation. This study also examines literature related to towers' behavior against environmental influences such as wind and temperature. Now, drawing upon the aforementioned studies, the main problem lies in the noticeable lack of focus on transmission towers when it comes to fully automated OMA. Aside from the primary gap, we also identified several additional problems from different literature, including limited validation of random forest, insufficient studies on environmental effects of transmission tower, and the scarcity of local research on these critical structures. Therefore, this paper aims to contribute to the existing discussion by applying a machine learning algorithm to methods by Rosa et al., supported by other objectives including the evaluation of other machine learning performance, verify accuracy through FEM comparison, and analyze field and simulated data, and also to demonstrate the impact of environmental variability. Okay, so in general, this study aims to support the improvement of transmission tower safety and resilience by applying a data-driven approach for automated model analysis. Additionally, this study takes an initial step or aims to provide initial insight that could inform future discussion on developing specific design standards for transmission tower in the Philippines, which are currently not covered under the NSCP. Here are the scope of the study and also the conceptual framework. So the study is structured into three main stages. So first, we have the pre-validation stage, referred to as PV stage, field implementation, and the variability analysis. Here's the closer look of the simplified flowchart for this study. Two types of data will be analyzed. The first one from the analytical model and from the field experiment. Okay, so the structure of interest is a 230 kV live transmission tower operated by Pinelco and Orion Bataan, and it has a total height of 38 meters. So the field monitoring system consists of accelerometer and anemometer, and other equipment used for the field test are also shown here. So the sensor placement is shown in the slide. So a total of 8 sensor location and total of 16 uniaxial sensors were used for this study. For data pre-processing, we perform data cleansing, signal filtering, and data reduction using singular value decomposition. Now for the system identification, equations used here are from Rosa et al. 2020 paper and its open access script. So the SSI Cove algorithm is the primary model analysis method used in the study. And to automate SSI and not to assume the values of the control parameters, the quasi-Monte Carlo approach is used. So with this method, the user only needs to specify the number of simulation. Stable model results are distilled from the stabilization diagram using the stability criteria equation, and the extraction of the physical poles from possibly stable poles is accomplished via kernel density estimation. Each machine learning models predicts which combination of the control parameter for the SSI algorithm is able to provide good model estimates. Afterward, new quasi-random samples of the control parameter for the SSI Cove algorithm are generated repeatedly until statistical convergence criterion is achieved. Out of many machine learning models available, this study focuses on just 4. So we have random forest, XGBoost, K-nearest neighbors, decision tree. So we'll refer to them as RF, XG, KNN, and DT throughout the presentation. Each model has its own strengths and limitations. Two are optimized for fast prediction, while the other two, KNN and DT, are known for their simplicity. Okay, so the Python classification report is used to evaluate the performance of each trained model using this evaluation metrics. So the results will be cross-verified using established SSI methods. So damping ratios obtained from the field are also used for finite element updating, which is then compared against standard code assumptions for validation. So this method was also applied to validate vibration data collected from the Carillon Tower. Okay, so for the results of both PV and FY stage, specifically the performance of each machine learning model, we can observe here from this table that phase 2 runs faster despite generating more simulation than phase 1. So this supports the fact that it no longer needs to rerun the entire SSI process for each simulation, where only predictions are made based on the output of phase 1 simulations. So runtime for FI stage is slightly higher than for the PV stage due to increased complexity and variability in the field acceleration data. The longer runtime for KNN and DT in both stages is attributed to extensive sampling needed to obtain the target feasible sets. So in this slide, both RF and XG models maintain high accuracy with 100%, but this value dropped to a descent of 98% for both training and prediction. This decline can be attributed to more random dataset of field data that resulted in less identifiable model peaks. Okay, so for confusion matrices, we see that XG and RF produce true classifications only, indicating a strong capability to correctly identify visible sets. Similar trends were also observed for the FI stage, where these models maintained high true positive rates and true negative rates with minimal misclassification. Now, moving into the dynamic characterization, for the monitored signals, the PV stage plot on the left shows relatively uniform signals across all channels, reflecting the controlled condition, while for the FI stage, it appears more scattered and irregular. For the singular value decomposition of the power spectral density, for PV stage, it presents a distinct and clear peaks, while the FI stage exhibits a PSD with less pronounced peaks. Comparing the overlap stabilization diagram of two stages, the PV stage clearly shows distinct model peaks similar to the monitored signals, which are more easily distinguishable than those from the field vibration data. Now, the stabilization diagram shown here illustrates the model characteristic of three different structures from different studies. So, for the suspension bridge and tall buildings, it displayed denser cluster of modes, especially at lower frequencies. In contrast, the transmission tower of this study shows fewer order, but still distinct modes, which is also related to the quality of the sensor used. KDE plot for PV stage show only less number of peaks, and these peaks are almost the same as the results from the FEM. The KDE plot for the FI stage shows numerous identified modes even with the use of automated model analysis. Hence, we can say that the quality of model identification heavily depends on the informativeness of the collected vibration data from the field. So here are the numerical values of the model frequencies extracted from KDE under PV stage, and this one shows the numerical values for damping. From the field measurements, several closely spaced modes were not detected by traditional SSI techniques. This limitation is also evident in the damping values, where some values are missing due to inability of conventional methods to capture certain modal frequencies. For most modes, noticeable trend can be observed where damping values tend to decrease as the mode number increases. So this graph reveals that both RF and XG have the most modal number that is closest to the FEM result. Differences in damping ratios between models show that XG consistently matches random forest. Comparing the numerical model results for PV and FI stage, the frequency values recorded during the FI stage correspond well with those predicted by the analytical model, with percent differences ranging from 0.22% to 1.64%. Significant discrepancies are evident in the damping ratio, with the most substantial difference reaching up to 139.14% in mode 2. Okay, so for benchmarking, there are no specific code recommendation for frequency values. So instead, we compared our result with those from the other studies. The first fundamental frequency identified closely aligned with the expected value of 3.8 Hz, while the measured damping ratio value for the first mode remained below ASCE 74 recommendation of 4% and fall within the range specified by other international codes. Shown in here are the MAC values or model assurance criterion values from random forest, with average MAC values ranging between 74% to 81%, which are in good agreement if we compare them to other similar literature examining analytical versus field data measurements. So this slide shows the finite element model updating results from ETABS, where the model with 1% damping showed the highest displacement and forces as expected, highlighting the importance of accurate damping assumptions to prevent over or under design. Now for the variability analysis, random forest and XG were faster and more efficient than KNN and DT for 120 2-minute data segments. However, what is shown from the previous slide is not the case for a lower number of sensors. This graph shows that for simpler, smaller scale application, decision trees efficiency is good, but drops with increasing data volume or number of sensor channels that need to be analyzed. So for this one, it shows the average values performance score, which reveal the strong performance of RF and XG over other models. For continuous monitoring, the frequencies and damping ratios remained broadly consistent throughout the testing period, while the coefficient of variance or COVs for frequencies from 120 observation show minimal variation, and RF demonstrated stability with lower COV values followed by XG. The COVs for damping ratio are significantly higher and more widely spread than those for frequency, with values spanning from 2.02% to 7.02%. As the study is conducted during the period of stable outdoor temperatures and the thermal recordings were made at one specific location only, the correlation of temperature with both frequencies and damping ratio is notably weak. Only the correlation values of two modes such as mode 1 and mode 3 were found to be statistically significant. Like the stable temperature readings, the wind speed values were consistent throughout the measurements as well. And only two modes, specifically mode 3 and mode 4, showed statistically significant correlation, which may also be attributed to the structure being stable during the measurement. And this observation can serve as the basis for further investigation. While for the damping versus frequency relationship, the scatter plots show mostly flat trends, suggesting weak correlation across all modes. For the final evaluation, so this table summarizes the performance of 4 machine learning models based on the several key metrics. RF generally leads across most criteria. XGBoost also performs well. Now, for some general conclusions for this study, the study confirms the feasibility of automated and intelligent model analysis for structural health monitoring of transmission towers. Results from the field-based OMA for this tower showed good alignment with FEM results. Random forest stands out among the machine learning models tested, and the damping values obtained from the field still remain within international code limits despite showing greater variability. So this study, while offering valuable insights, had several limitations that future research can address, such as future studies should install sensors on higher and diagonal parts for complete mode shape reconstruction. To perform long-term data collection under varying environmental conditions, such as nighttime temperature drops, fluctuating wind speed, and many others. Future research can explore hyperparameter tuning techniques, including Bayesian optimization, to enhance computational efficiency and accuracy of all models. Number 4, the use of higher sensitivity sensor. And the fifth one, future studies could adopt more robust noise filtering and signal enhancement methods to improve the quality of input data before running SSI. So all in all, this study highlights the effective integration of analytical simulations with real-world field data, paving the way for more resilient and data-driven infrastructure monitoring systems in the Philippines, especially for transmission towers. So here are the references used for this research. And thank you for listening.
Again, for the attendees, if you have questions about the presentation of Engineer Samudio, please use the Q&A feature of Zoom. Yes, I would like to present the certificate of appreciation to Engineer Roydon Jude Samudio for sharing his research expertise in the 2025 Graduate Research Colloquium. So given this 25th of April, 2025 at the Institute of Civil Engineering, University of the Philippines, Diliman, signed by Dr. Jose Regine F. Regidor, Director of UP ICE. Okay. Okay, so we can now move to the last presentation for today. Our third presenter, Engineer Melvin Raymond G. Dangin, finished his Master's of Science in Civil Engineering, major in Water Resources at UP Diliman in 2024. He currently works as a water engineer at the USC Water Resources Center Foundation Incorporated and teaches at the University of San Carlos part-time. His research interests include hydrology, hydrogeology, flooding, and water supply. So let's hear the presentation of Engineer Dangin. Engineer Dangin, you may start.
Before I begin, I would like to check if I'm echoing of any sort.
Your audio is working well.
That's good. Okay, so good afternoon, everyone. It's a pleasure to be able to finally present my master's thesis. And I'd like to thank, first and foremost, this wouldn't be possible without the support of the DOST ERDT scholarship, and most especially this guidance that Dr. Eugene Herrera, my advisor, has given me all throughout these years. Okay, so the title of my study is Coupled Surface Water and Groundwater Modeling for Water Supply Assessment. It's the case of Mananga Watershed, Cebu. So it's very good that this GRC is being held online because I'm from Cebu. I'm currently presenting from Cebu. So that's all made it possible. In here, similar to Manila, we have an increasing population, which directly affects the water demand. So more people, more water requirements. It's been steadily increasing for all cities and municipalities that belong to the Metro Cebu, which is 7 cities and 6 municipalities. Right now, we're over 3 million population. And that's been increasing, which affected our water demand, which now reached above 500,000 cubic meters per day. So with that, right now, it's almost 200,000 cubic meters per day, or 300 even, to the deficit with respect to the Metro Cebu Water District's supply. So with that, where are we getting our water here? Locally, we're heavily reliant on groundwater, actually. That's 70% of our supply. And unlike Manila, Manila has stopped its water pumping several years ago. Here, it's still ongoing, and it's increasing our risk on saltwater intrusion and all other effects. And with that, but we also have other sources, and in this case, surface water, but just accounts for like 20%, and brackish. Although here in Cebu, our saltwater sources, in a sense that we're doing desalination, has been increasing for the past years due to new players coming in, private entities acting as bulk water suppliers to the water district. So, but as of the moment, we don't have much surface water sources, which our current ones are very much affected by other, say, El Nino and other heat phenomenons. So with that, increases our risk for ground water supply challenges, such as the saltwater intrusion and also nitrate contaminations as well. So we've been exploring here. There are several watersheds that we could tap onto that is very nearby the Cebu City area, and one of which is the Mananga watershed. Mananga watershed is just adjacent to the Cebu City. Its mountain area is actually part of Cebu City, while the downstream area is in Talisay. So it's the neighboring LGU. So it has relatively small watershed, 8,600 hectares. And throughout the years, since 1986, it's been studied and it's been reviewed and verified. Even international organizations helped us to really establish this as a water source, even groundwater modeling, but still we haven't really caught on into implementing it, other than the Haklupan facility, which is in the midstream of the Mananga watershed. It's essentially a weir that allows water to backflow towards an infiltration basin, and water is then naturally filtered and pumped out eventually for use. So that accounts for like 33,000 cubic meters of supply water per day. But still, that's very small compared to our water requirements. So Metro Cebu, with its insufficient and highly vulnerable water supply to extreme climate, evident to the problems like growing water supply deficit, reliance on groundwater, existing surface water sources are unreliable for extreme dry periods, and the declining groundwater levels. Now, there's little research done on the interconnectedness of these two water sources, because what we dream is to have more conjunctive use of these two resources. Ideally, we want to use our surface water during the time when there's a lot of rain and save our groundwaters for the dry periods. So that's kind of the dream, and that kind of setup is not fully or maximally explored in our setting. So this research aims to understand the connection between the groundwater and surface water in our watershed. To evaluate that, we created SW surface water and groundwater model, which is a watershed scale, and to analyze the effects of upstream reservoirs to our downstream aquifers, and to investigate possible water resource management scenarios. So later I will just brush through them because they're quite plenty and I not have enough time to discuss. But just a quick background: surface water and groundwater more often than not are connected, especially through their rivers. Rivers are either effluent or influent, or gaining or losing. So when the groundwater level surrounding the river, neighboring the river area is higher, it tends to feed towards the river. So now that river can be coined as a gaining stream, whereas if the groundwater level in the adjacent areas of the river network is lower than that of the river water level, then the river recharges towards that aquifer. Now it becomes a losing stream. So this actually has been long studied by multiple research, and through coupled modeling approaches, various developers have been pursuing this. And the more stable ones is the more popular softwares have been coupled together, which is the ones that is used in the study, the soil and water assessment tool to model our hydrologic regime. So it's a semi-distributed approach where it uses HRUs, or the hydrological response units, where in each unit they're lumped together with the same qualities, and that's where you solve for the soil water content for every time step. And for the groundwater, it's ModFlow. It's more of an industry standard at this point, that it solves for heads for your groundwater, but it also solves for the three-dimensional flows for porous media. So now these two powerful models have been coupled many times, and this one is the more recent development where SWAT and ModFlow have been coupled, that where the stream flow would either recharge or discharge depending on its neighboring water level, groundwater level. And also with that is incorporating well pumping, and even the possibility of using reservoirs for your simulations. So yeah, for the modeling framework, essentially the inputs, there are two sets of inputs: the ones that we use for the SWOT model, or the hydrologic model, and the ones that we use for the groundwater model, or the ModFlow. So both uses digital elevation models, although the surface one uses the land use, soil cover, and even weather data. So I'll just scan through them later. And for the groundwater model, still uses DAM, but now focusing on what's underneath our soil, so the geology. Now we want to know the pumping rates of the wells and also the boundary conditions that would serve that. So recharge actually would come from the SWOT simulations, and then it will be fed into the mod flow as that response back to our rivers as well. So outputs, yeah. So the model would essentially show us the discharges or the queues of our rivers and or the river network, and then the water level of the groundwater level, and also the more unique feature of surface water and groundwater interaction, whether it's a losing stream or gaining stream. And finally, the water balance, which we know we could get a macro sense of whether we are managing our watershed or water resource in a very holistic way. So actually, these two models could be developed on parallel if we have more people, but when I did it on my own. So it's just essentially linear, but they go by the same phase of gathering data, setting up the model, making sure that all data inputs will be prepared that the model could read. And then you run the simulation, you calibrate it to meet real world data, and essentially you get a baseline model where you run multiple scenarios from. So these are the data inputs. I'll just run through them. Data elevation, land cover, soil cover, and then geologic maps, where we consider this is where we base our layerings with in terms of depth, in terms of the type of geology, how many layers are going to be implemented, things like those. So, and the bread and butter of any hydrologic model is the rainfall. We are very much lucky here in Cebu that the Metro Cebu Water District, in partnership with the Water Resource Center Foundation, has been collecting this data set since 1975. And for this study, though, we are just using the 2010 to 2019 because the land cover data that I intended to use was just 2015. So just to simplify, and ideally you want to have multiple land cover change to incorporate that, but that's beyond the scope of my study. Temperature and relative humidity as well is incorporated because of other inputs for your meteorologic models. So river discharges, this is the data that we want to some sort of mimic in a sense. So we calibrate our model based from these observations and optimize these parameters. Well locations and well logs. Abstraction rates is very important. So at least in this case, there's a limited amount of data that we could use on this, but from verified sources, these are sufficient. And then the piezometric levels, where we also compare our groundwater data from, so we know how true it is. But if we see that the simulations are close to what is in reality. So the SWOT model setup are as follows. Created 23 subbasins, and it had a warm-up period, very lengthy warm-up period, just to accommodate the groundwater simulation. But essentially, calibration period is 6 years and validation is 2 years. So for the model setup for ModFlow, in the same way, it follows the same periods for calibration, warm-up, calibration, validation, and has the following boundary conditions as you see in the table on the right. Okay, so these are the results, in a sense, the baseline results of the hydrologic model. We got a fairly satisfactory NSE, or Nash Truth Efficiency factor. The 0.5 is, you would think about it as pretty low, but actually in hydrologic studies, it's fairly satisfactory. And we validated it and had similar NSE as well. So these are the parameters on the right that are sensitive and were calibrated to find our water balance to be from 100% of rainfall. That's 1,800 millimeter of rainfall. About half of that goes to the atmosphere through evaporation, and then a little more than a third is runoff or goes towards streams, and groundwater flow is 6%, while percolation or our recharge to the groundwater is 9%. As for the groundwater model, this is the result. The most sensitive parameter is the alluvial hydraulic conductivity, followed by the Carker limestone hydraulic conductivity. So all of those, essentially K values are the most sensitive ones, except for those that are large and more aged geologic formations. They're pretty low. So our groundwater budget, or the groundwater balance show for the full period is there's a negative change in storage. Essentially, we're pumping out more water than what is coming in. So that is actually kind of sounding the alarm that we're not very much sustainable in using this watershed. So what we also want to see is primarily how groundwater levels change with respect to its season. So during wet season, it's very clear that the rivers are gaining because water levels are flowing towards the river. Whereas during the dry season, it will be difficult for that to happen, although there's still signs of that. But there's a cone of depression is more pronounced in this, meaning since less water is coming in, and pumping tends to get increasing because it's dry season, it's got a hot, people tend to use more water, unfortunately. So the cone of depression becomes more pronounced in that time. And finally, for the surface water and the groundwater interaction, this is very interesting because for some of the literature have said that Mananga watershed is a losing stream, but this study shows that it's actually varying spatially throughout the river network. So some parts are gaining, some parts, which is somewhere in the upstream, if you can see the green circle, and the red circles indicate where there's a losing stream or water is being discharged towards the aquifers. So with that kind of model baseline, we can now run scenario analysis. So for this study, I ran 5 simulations where one actually tries to meet the supply by increasing, it meet the supply deficit by increasing abstraction rates at the downstream area. So the Mananga well field, as we call it. And the second scenario is we meet the demand in the future by increasing the abstraction rates at the midstream. So in this area, the Haklupan wells. And scenario 3 is increasing the weir height. So the intention of that is to increase its capacity and hopefully increasing the production as well. So that's scenario 3. Scenario 4 is just a combination of 1 and 3. And then scenario 5 is now considering Mananga Dam and the reservoir, how would it might affect our groundwater downstream. Okay, so for scenario 1, the results show that when we double the pumping rate just to meet the deficit, there's a huge change in our downstream aquifers. It could reach up to 7 meters. The change of the groundwater level could go as much as -7. And for scenario 2, if we want to increase the abstraction rates midstream in the Haklupan facility, it wouldn't actually cause much change to the downstream groundwater levels, interestingly. And scenario 3, we wanted to try and increase, and as actually recommended a future study by Kawo in 2018 to increase the height of weir 2 and 1 by height of 1 or 2 meters. This shows that by increasing so, other than you increase your production, you could also increase the groundwater levels downstream, as shown in this figure. So there are like 1 to 2 meters increase. downstream. And the combination of two would just actually show the same behavior but offset because of the weir increase. Now, the more interesting one is the Mananga Dam Reservoir. So this is an attempt to model that development. Mananga Dam and Reservoir could potentially actually decrease the groundwater levels, as the simulation shows, of downstream aquifers, not because they are in the same hydrogeologic environment, because the Mananga Dam is in a different geologic formation, but because there is a decrease in river flows. When you build a dam, you try to trap water in and just release whenever, number one, it's the 10%, the minimum net 10% environmental flows, and number two, if you have so much water and there's an upcoming flood, an upcoming storm, so you need to have a buffer, so you have to discharge on that. That's what happened here in this diagram, where there's an increase of flow somewhere 2017, early 2017. So for groundwater level, there's a change in terms of its baseline elevation, as well as its response to the natural rainfall seasons and the droughts. So in summary, with the SWOT model flow model developed, we are now able to understand the interconnectedness of the surface water and the groundwater. We're also able to find out the water balance in the watershed, both for surface and groundwater. Also, we also were able to find out that groundwater obstructions have huge impact in our surface and subsurface water connectivity. Geology, I would say, plays a crucial part in defining how we should be able to do integrated surface water and groundwater model. This study actually offers a gateway towards a coupled, a conjunctive use of these two resources should it move further. And recommendations, essentially, we could actually allow Haklupan weir to be raised in order to increase production and also the downstream aquifer. And for future researchers, gathering of primary data is very much necessary in this case. I was doing this just based on secondary data, but doing primary data collection gives you a better feel of how you model your area. So it is very much imperative that the modeler who will do a coupled simulation in this case should be well versed in both SWOT and ModFlow separately before engaging into coupling these two models. So yeah, I think that is all for my presentation. Thank you very much for your attention. Apologies for the time extension.
Okay, thank you, Engineer Dangin. Again, to the attendees now, if you have questions, so please use the Q&A feature of Zoom. No, I already see a number of questions being inputted. Okay. So allow me to present this certificate of appreciation to Engineer Melvin Raymond G. Dangin for sharing his research expertise in the 2025 Graduate Research Colloquium, given this 25th of April, 2025 at the Institute of Civil Engineering, University of the Philippines, Diliman. Signed by Dr. Jose Regine F. Regidor, the Director of UPICE. Okay, so now we move to the question and answer part of this colloquium, and allow me to read some of the questions and for the presenters to answer them live. No? Okay, maybe first question coming. Okay, hindi ko lang ma-open. First question to Engineer Sagid from Mr. Sapo. Can you please further explain the advantage of your study in real-world applications?
Yeah, so the approach I developed, excuse me, rinig ba?
Yes, yes.
Okay, sige. So the approach I developed focuses more on the macro scale deformation response of structures. So if we were to try and accurately analyze offshore structures like bridge piers or flexible breakwaters and the like, we should not actually convert water into its equivalent force distribution, but rather analyze the system as a whole. So we should account for fluid structure interactions. With that, we are then supposed to analyze the problem using combined FEM and FVM as of status quo to properly address the FSI phenomena. However, if we are only interested in macro scale deformation like uplift and toppling, using the method I proposed skips the tedium of discretizing the structure as thousands of finite elements and instead let us discretize as more countable rigid bodies interconnected by springs. So ayun siya. Basically nire-reduce natin yung computational load para ma-discretize natin yung structure. So ayun.
Okay.
Thank you sa question.
Okay. Thank you, James, for answering the question. So I'll be reading another question directed for Jude. No? In what ways do automated methods such as machine learning algorithms enhance the efficiency and the scalability of analyzing large vibration datasets in structural health monitoring?
Okay, so very important yung pag-use ng automation when it comes to handling large vibration data because we can reduce the amount of time of simulation. Like for example, from my presentation, from the result for phase 1 for 100 simulation using running a complete SSI algorithm, it took 2 hours. And while for the phase 2 for the prediction part, even though we simulate 2,000 different control parameter simulation, the runtime is almost the same lang. So that's the importance of automating the vibration data rather than completely doing the same simulation all throughout. I think that's
So thank you, Jude, for answering the question. I saw a question for Engineer Dangin in the Q&A. Would you like to answer that live or I
Yeah.
saw that you're typing? Okay.
It's okay.
So,
Actually, I'm actually typing, but it's okay. I could
so
answer.
maybe you can read the question also.
Yeah, okay. So the question actually is, what are your findings on the relationship between the level of cone of depression and the frequency of commercial and residential facilities in the area? Actually, for my study, the cone of depression was mainly driven by the water district's pumping activities. So commercial and residential facility water demand were not really considered in the simulations. So I guess that adds bit more complexity, I would say, because private wells, if there are other people pumping in there, is very difficult data to acquire actually. So yeah, the cone of depression, but generally speaking, MCWD or the water district are one of the major abstractors of groundwater since they are the ones who could dig deeper wells, have bigger pumps. So that's why we focused on them.
Thank you, Engineer Dangin, for answering the question. Another question for Engineer Sagid. No? Why combine the modified rigid body spring method and the smooth particle hydrodynamics method specifically in a staggered coupling scheme? What makes that pairing worth exploring?
Thank you. So the combination was chosen because both methods are discrete and lightweight. They both convert the physics of the problem from continuous materials that obey solid and fluid mechanics to discrete models that instead obey particle and rigid body kinetics. So the staggered approach allows them to basically do their own thing individually, and only require output from the other, not having to weave into the intermediate solution steps. So the focus then shifts to managing the interaction, which is easier to control and test rather than trying to build a single monolithic model from scratch. So ayun, pinapadali niya yung analysis dahil pinapalitan niya yung physics ng problem. Well, not necessarily pinapadali, pero kino-convert niya. Pinapalitan niya yung problem statement, kumbaga. So ayun ang nangyayari.
Okay.
Nasagot ba yun?
Okay. Thank you, Mr. Sagid, for answering the question. Another one for Engineer Samudio. So how does the location of sensors on the structure affect the accuracy of the identified modes?
So I think the placement of sensors are very important. Like for this study, we only place the sensor at the lower part of the transmission tower where we expect for a typical flexible structure, we expect that most of the displacement will be at the topmost. So it will have an effect, a significant effect if we do have that recording from the topmost. So since we placed the sensors on the lower part, so the vibration data recorded, the model results are not that strong. Now they are although we gathered the important one, but I think for the other types of behavior like the torsional effects, it was not able capture that the behavior for torsion and other types of bending, higher order bending. So this is the importance of having the complete location for mode shape construction.
Okay. Thank you, Mr. Engineer Samudio, for answering the question. For Engineer Dangin, a question is, can you expound more on the model's applicability for saltwater intrusion?
Yes.
How was the Mananga Dam incorporated in the model?
Okay, so actually, saltwater intrusion, although it's a very pressing issue and has been monitored since 1975 here in Cebu, was not considered or applied in my work because it kind of adds complexity, whereas we wanted to focus on how things are interconnected. But for future researchers who are interested in pursuing this topic or in this study area, it is actually possible to extend it further. So I was able to cut my hydrologic model up only to the well field. So that at that point there's some intrusion, but it's not as high as when you will go beyond, we go further towards the coastal area. So at that point, factors like seawater level comes into play. Also the calibration of saltwater content, chloride also comes in, but luckily MudFlow has a saltwater intrusion module for that. So yeah, it's a good research to pursue for others. And as for the Mananga watershed, the Mananga Dam, it's a very simplistic approach of simulating dams through the SWOT module of dam element.
Okay, so thank you, Engineer Dangin. I think those are all the questions that we received in our Q&A. And yeah, I think with that, we can already close the Q&A session. And yeah, so with that, I would like to thank the presenters now for giving time, sharing your outputs of your research, and for with the attendees, I would like to congratulate you in completing the MS program. Okay, and okay, so before we close the colloquium, so I would like to acknowledge the assistance of the ICE Graduate Program Committee, the ILC Diliman, Dr. Hill Cruz, and Assistant Professor Leah Diola. And yeah, the attendees, please refer to the link that's being flashed now, or scan the QR code that I'm showing now, and give us your feedback. So with this, I would like to officially end the colloquium. And again, thank you for attending, and see you in the next colloquiums that will be hosting in the next few months. Okay, thank you for your participation.
Thank you, sir.
Thank you.
Thank you, Doc.
Thank you.